Okay. Now, having said and talked about thermodynamics as well as fluid flow or fluid dynamics, we will now move on further and talk about the next segment of the science base of steel making, which is heat transfer. Now, thermodynamics, as we have seen, will allow us to predict the feasibility of a process. We can perform many equilibrium calculation and get good insight of what is happening within a steel making system. And fluid flow, as we have seen, particularly all the liquid state processing operation involves some kind of a fluid motion. So, knowledge of fluid flow is also important, as it will be more and more evident in order to calculate the rate of the processes, which is of our prime interest. But by now, I think you have been able to appreciate that to handle with thermodynamics, to handle with fluid dynamics, one has to have very good analytical capabilities. A good background in mathematics is a prerequisite. So, never ever think that steel making is a highly qualitative subject. It evolved as an art, but today it is highly scientific, and we have to have good analytical and mathematical abilities in order to really move further. Now, moving on to the next segment, which is heat transfer. I must first explain to you that what is the relevance of the subject, and as you all know that large tonnage of ferroalloys and deoxidizer elements as well as steel scraps are routinely added in molten steel, and these solids, which are invariably projected into steel at room temperature, there is going to be thermal interaction between the this added solid as well as the melt, because they are at the similar temperatures, and as a result of which the alloying additions or various deoxidizer additions will proceed to melt and then dissolve in steel, and the overall rate of efficiency of these addition techniques depends on the rate of heat transfer as well as the rate of mass transfer. We will discuss these in succession. But apart from that also, when we are talking of particularly solid state processing operation, for example, solid state processing operation implies beyond continuous casting, which involves slab reheating, then rolling, then you have galvanizing, and all these operations are carried out at relatively high temperature, where the prevalent temperature plays a very important role in terms of the efficiency of the processes. For example, if you have a furnace, and in this furnace, if I have kept an ingot, for example, this is an ingot, and this is a furnace at a temperature of T, and then the heat. So, Q is flowing from the furnace, and this is the furnace. I write it as Fc, and so Q, heat is transferred into the ingot via several mechanisms, which we are going to discuss in a minute, and then as a result of this transport of heat, the object temperature continuously increases. Now, the rate at which the surface temperature increases and the rate at which the inside temperature increases are dramatically different, because of the resistance of solidified or solid metal, solid material to heat flow. Now, if you want to predict the homogenization time, suppose I have an ingot and I place it within the furnace, and I want to now find out that at what time the ingot has become completely homogeneous, and it is only then I am going to take out the ingot from the furnace and subject it to either soaking pits, or where the same temperature is maintained, or straightforward taking it to the rolling mill. So, prediction of complete homogenization time or an uniform rolling temperature in the reheat furnace is of key interest, and unless we know the fundamentals of heat flow within the furnace itself, from the furnace environment to the solid surface, and then within the solid surface, we will not be able to calculate the optimum reheating time, which essentially gives a constant reheating, constant ingot temperature at the end of the cycle. So, innumerable descriptions can be given where heat transfer can be shown to play decisive role. So, there is no doubt that we will have to have good background of heat transfer in order to tackle efficiency of many metallurgical processes. Roll, and the slab is moving between the rolls. There is going to be a contact resistance, there is going to be heat flow from the roll is going to be cooled, and then the slab is moving between the rolls, and the rolls are going to take away. So, you have the direction of movement is like this, and then the the rolled product comes out like this, okay, and we have enormous amount of heat flow between the roll surface and the solidified material, and also because of mechanical working, some amount of heat is going to be evolved, just like the way heat evolves during solidification process. So, we have heat transfer from this, heat is being lost by various mechanisms. Then there is heat evolution within the solid because of mechanical working, conversion of mechanical working to heat energy, where there is a efficiency factor is involved here, and then because of the contact between the roll, and this roll is always water cooled to maintain a relatively low temperature, to maintain its low deformability, deformation, and to maintain or to have good heat transfer rates. So, we have heat flow from the solid surface into the roll. Okay. So, all these things, the heat loss to the environment, the heat evolution due to mechanical working, heat flow to the roll, and all these things are going to determine the overall temperature at which the rolling is going to be carried out. So, if you want to predict the evolution of temperature within this, it's a very complex task. You have deformation taking place, you have heat transfer taking place. Of course, there is no fluid flow, but there is solid flow here. Okay. The volume remains constant, but the dimensionality of the object changes. So, it is a horrendously complex task, and in order to predict that at what temperature the slab is going to come out, you have to have good background of heat transfer and mechanical working process or the deformation theory. So, I can go on, and before I really end this part, I would now like to show that, well, we are talking of heat generation, we are talking of heat flow, we are talking of heat flow between the roll and the solid, and there are various mechanisms by which the heat flows actually, and we have to discuss first the mechanisms of heat flow, and then possibly we will be able to tackle this sort of a problem or this sort of a problem. Now, there are three fundamental mechanisms by heat flows from an object, and within a solid object, the primary mode of heat flow is called heat conduction. As I said, the primary mode, it is the only mode of heat flow within the solid. In the solid, no other mode of heat flow can be there. Now, when heat flows from the solid to the ambient atmosphere, it can flow via three different mechanisms. It can flow via conduction, and there is a second which we call as a heat convection or convective heat transfer, and then finally we have heat radiation or radiative heat transfer. Heat conduction, which takes place within the solid, is because of a material property which is known as the thermal conductivity of the material. If there is no thermal conductivity, there is no heat flow within. So, heat conduction basically is a diffusion process, just like the way mass flows from one region to another region because of the property mass diffusion. So, heat conduction is also termed as diffusion of heat. We must remember that there is a diffusion of momentum, and the diffusion coefficient of momentum is viscosity. The diffusion of mass, for the diffusion coefficient is the mass diffusivity, and diffusion of heat, for which the diffusion coefficient is the thermal conductivity, or you can interpret it as thermal diffusivity, which is K divided by rho C. So, this is actually thermal diffusivity. Then we have mass diffusivity and mu by rho, and this is the kinematic viscosity or momentum diffusivity. And the properties which are responsible for diffusion are basically thermal conductivity, mass diffusion, and viscosity. Convection, on the other hand, as the name suggests, requires some flow. So, if there is no flow, there cannot be any convection. So, as a result of fluid convection or movement of fluid, we can have heat flow in the system from one point to another point. For example, I have a solid here, solid is moving here. If there is some motion here within the liquid gas phase, so this is an ambient, this is called as an ambient or the atmosphere which is above the solidifying. So, this is the slab which is being rolled, slab is made into, and the We have got either a thin slab which is coming out or a strip which is coming out. So, heat will be lost from here to here, okay, and we can ambient, and if you have a fluid motion here, if the flow is going like this, so this flow of air, if the ambient contains air, can take away some amount of heat, and the flow of heat because of this fluid motion is termed as convection. While conduction and convection requires a material medium, radiation does not require a material medium. For example, the heat that we get from sun is through radiation, okay, it does not require material medium, and there are certain laws which you must first understand in order to move on further. So, the rate laws of which you also call constitutive equations. So, these rate laws are important, that if heat conduction is taking place within the solid from this point to this point, therefore, flow of heat from this point to this point is going to be purely by conduction. Now, the heat is flowing by conduction, I must be able to know that at what rate heat is flowing. That is the most important, and then only possibly I can talk of that what is the homogenization time of the ingot. So, heat conduction, we have number 1. So, I am not going to write it again. So, it is Fourier's law. As we all know, the Fourier's law is nothing but the heat flux Q along the x direction is equal to K temperature gradient. Okay. This is a vector quantity which is a heat flux, this is a thermal conductivity, and this is. We can similarly write the heat flux along y direction. The definition of flux all of you must be knowing. It is the amount of energy, heat flux is amount of energy per unit area per unit time, and that the area is normal to the direction of heat flow. So, heat flows from a region of higher temperature to a region of lower temperature, and that is why it is preceded by convention a sign of negative. Now, this thermal conductivity, a material, for example, I can have a Qy, I can have a Qz, and in that case I may not have K in all three directions. K may be a direction sensitive property also, or structure sensitive property, and in that case, if the structure in this direction and structure of the material in this direction are not identical, we can anticipate that thermal conductivity in different directions can be different. If thermal conductivity are same in all directions, then we say that the material or the thermal conductivity is isotropic. On the other hand, if thermal conductivity is different in different direction, x direction we have Kx, y direction we have Ky, and z direction we have Kz, then we say it is a non-isotropic material. Now, based on this rate equation, that the generalized heat conservation equation is derived. Okay, the generalized heat conduction so, in order to calculate the flux, I will require that flux is, as I said, at what rate temperature is flowing from this point to this point. Okay. So, therefore, in order to know that, I have to know this distance, and I have to know the temperature difference T1 minus T2, and then only I will be able to calculate flux, and then only I will be able to calculate that at in 10 minutes of time how much of heat really has moved from this point to this point. Okay. So, therefore, the first and the foremost thing is, while the object dimension is known, I have to map the temperature field. Okay. I have to know the T field, and it is only by knowing the T field I will be able to temperature field, I will be able to calculate the rate of heat flow from one point to another point, and then only I will be able to tell that, well, such and such is the homogenization time for the ingot and so on. On what basis the temperature is calculated, where from we obtain the temperature? The temperature is known from by writing a thermal energy balance equation. So, basically this also you have done. I am going to just mention, if you take a control volume and then you say that, well, in that particular control volume we have heat flow along three direction, heat is flowing, but due to conduction in x direction it is leaving on this particular face, for example. So, it is entering on this face, this is the phase that I am talking about, and this is the phase I am talking about. So, into this infinitesimally small control volume, heat is entering as well as heat is leaving. If we do it in 3 different directions, how much of heat is coming in, and the net difference of this, that is between heat flowing in and between heat flowing out and heat flowing in, will determine whether the temperature has increased or decreased. Okay. Also within the control volume, we may have a thermal source because of maybe a phase transformation reaction, because of maybe a mechanical working process. Okay. So there may be some heat generation also. So therefore we can say that whether the net rate of change of temperature of the body is going to be determined by the heat flow, heat coming in and heat going out in 3 different space directions, as well as the rate of heat generation. And therefore the equation, if you balance this equation, write this equation, okay, in terms of what this means, that you have heat coming in minus heat going out in all 3 directions, plus or minus heat generated in the system is equal to net rate of heat accumulation. This is the statement, energy conservation statement in word, and if I use Fourier's law to convert this statement into mathematical form, this is what we have seen. Also you get a partial differential equation which looks in this familiar form. Most of you must be knowing what is this equation called. This equation in its so that is the generation term that I am talking about, thermal heat generation. If S is negative, then it is a heat consumption in the process, and this represents the net efflux of heat due to conduction along x direction, along y direction, along z direction respectively, and this is the heat accumulation term. Rho is the density of the solid under consideration, Cp is the, and this equation is basically written for constant density and constant heat capacity, although thermal conductivity can be assumed to be a function of temperature. As you see, I have written it for isotropic thermal conductivity, because along x direction also I have written K, along y direction is also K, along z direction is also K. So therefore I am essentially talking about an isotropic material, but nevertheless here the thermal conductivity can be taken to be a function of temperature, because I have maintained it within the bracket. Or alternatively, if we assume that it is a steady state process, so this term will become is equal to 0. If there is no heat source term, which is also equal to 0, and if K is equal to constant, in that case we can say that, well, it is or, which is a very popular equation. The name of this is the Laplace equation. So therefore, given the boundary conditions, now as you see, we have this is a second order term. So 2 constants of integration come from here, 2 from here, 2 from here. So given the source term, 6 boundary condition, 2 each for these terms, and 1 initial condition, I should be able to solve this equation. If I solve this equation, then I should be able to find out that what is the temperature distribution, and if I plot the temperature distribution as a function of distance, so I can know that, well, at a value of at certain time, at certain distance t y and certain distance z. So I can plot T temperature as a function of x, because temperature is a function of x, y, z and t. Now if I fixed time, if I fix z, if I fix y, which I have done as indicated, then I can see that, well, I can make a plot of t versus x, and suppose I get a plot like this. And how do I know this plot? Because I have solved this equation. So by solving this equation, I have been able to map the t, x, y, z and t field. This is now known to me. Okay. So I have governing equation is there, boundary conditions are there. I have solved this. Again, I would repeat, mention here that we cannot solve it analytically. We have to solve it through numerical techniques. Assuming that we can solve it, one equation, one unknown, given the thermal conductivity, given the source term, given the properties. Okay, it is one equation, one unknown. The unknown being T, which is called the dependent variable. and x, y, z, t are the independent variables, and if you solve this equation, we can get the temperature field, and at a fixed value of temperature time, fixed value of y, fixed value of z, I can plot the t versus x distance. And the slope of this line, which I can very easily determine, is nothing but, and this itself is a measure, multiply this by thermal conductivity, becomes the flux, and then I will know that yes, from this point to this point, at what rate it is really going. So, prediction of temperature, therefore, I can say that how can I find out the optimum reheat time? I will know, for example, my knowledge of heat transfer tells me that, well, the rate of heating at the center is going to be least, because it is, the heat has to reach from the furnace to the surface, and then it has to go inside the solid, and this is the conduction process, which is a molecular process. And of the three mechanisms of heat flow which I have indicated here, heat transfer by conduction is the slowest process. So, therefore, I can say that this center point, if my target temperature, okay, that I want, this is my optimum reheat temperature of 1100 degrees centigrade, then I can say that the surface is going to achieve this reheat temperature like this, and the center is going to receive follow the reheat temperature like this. So, this is the center point of the ingot, and this is the surface of the ingot. The surface is going to be heated much more rapidly. So, it is going to heat it up rapidly. As you see, the slope is more steeper, and therefore, it will approach the desired reheating temperature, which is the equilibrium temperature, which is the furnace temperature actually. So, the surface is going to attain that uniform temperature quite rapidly. On the other hand, the center is going to attain the reheat temperature or the optimum furnace the equilibrium furnace temperature at a much later stage. So, by monitoring the temperature of the surface, so I can now, having solved this equation, I will plot temperature at the center as a function of time from my numerical results, and then tell, well, it is after this time for such and such furnace condition I am going to get an optimum uniform temperature all through my solid, and the time required to attain that is going to be the desired or the optimum reheat time. So, conduction is very important for us, and conduction, for example, whenever we will have solids, conduction is the dominant or the only mechanism of heat flow. So, therefore, we will have to know, the physics of heat flow at the molecular level, the governing equations, the boundary conditions, etc., quite exhaustively in order to tackle the problem and make certain predictions we should be using, which would be of relevance to shop floor engineers and the designers as well. So, next we go on to convection. Now, convection, due to convection, heat flows over a large distance. Due to conduction, heat flows only over a small distance. You see, if you take a rod and then you put the rod, okay, suppose the rod is 2 feet long, and then one end of the rod you put it inside a furnace. Now, you are holding the other end, and the heat is going to take really much time, okay, to reach at this particular end, because heat has to flow within the solid rod, molecule after molecule. One molecule will pass on its heat to the next molecule, and that is the way it is going to reach, and this is a very slow process. So, you will see maybe after half an hour or 1 hour you are feeling some hotness at the other end which you are holding. On the other hand, imagine in a winter night you have put in a convection heater in your room to warm you up. So, the moment you put the switch, okay, and the fan as well as the heater in the blower goes on, you will feel that the heat is immediately coming to you, and therefore, we conclude that, well, it is the flow of heat assisted by fluid motion, which is the fan which is throwing the heat into the room, is much more rapid than the conduction heat or the radiation heat. Also, you can imagine when you have a rod, for example, usual old fashioned type room heater, okay. So, those rods basically heat flows from the surface of the coils to the ambient, okay. It is because of not conduction, not convection, but because of radiation, which is the third mechanism which I am going to discuss. So, for example, air conditioner, convection blowers which you use during the winter nights, these are typical example, and they demonstrate how heat can be moved from one place to another place or transferred over a large distance assisted by fluid motion. So, now if you set the fan speed at a lower level, suppose you are sitting at a at a distance and the blower is suppose a few feet away from you. If you set the fan speed at low level, then you don't feel, even though your desired temperature, the thermostat of the device may be at the right at the unit temperature, but you are controlling, you are only changing the fan speed. So, the fan speed is low, you feel that the convection heater, the heat is coming at a very slow rate. Now, if you increase the fan speed, you will find that heat is coming to you at a much faster rate. You are feeling warmth very quickly, and this tells us that the rate of fluid motion or the speed at which the fluid is flowing, that is going to play a very important role or determine the rate at which heat is going to go or be transferred from one point to another point. So, therefore, it is understood at this particular stage that before we can talk of heat convection or convective heat transfer theory, we must understand that we have to have some knowledge of fluid flow. If you do not know at what rate the fluid is flowing, in that case you will not be able to predict the rate of the convective heat transfer. So, we can say that if we look at this particular term, okay, multiplied by area. So, what is rho? Rho is kg per meter cube, U is meter per second, area is meter square. So, this term rho, U and A, this basically is nothing but meter cube cancel. So, this is actually the mass flow rate, which is kg per second. Then we have mass flow rate into Cp, this is C is Cp, and to T. So, this Cp is what? So, we have kg per second, and then we have Cp, which is joules per unit mass per degree centigrade, and this is per degree centigrade. So, therefore, this is kg and this is this. And this term basically tells us this is the rate of heat. This is joules per second. So, the rate of energy transfer. Okay, that is what is this particular term. So, this is the rate of energy transfer because of what? Because of fluid motion. I have not taken the differential temperature, I have taken the temperature of the fluid, and this is now there is a fluid motion, and therefore, this term, the rate of heat flow joules per second, okay, which is the dimension of this particular term, okay, and this joules per second or the rate of energy transfer from one point to another point is solely because of the fluid motion. And therefore, it is understood while I may have knowledge of rho, I may have knowledge of Cp, I may have knowledge of temperature also by putting in a device, but unless and until I have some knowledge of the fluid flow, I will not be able to quantify whether it is 5 joules per second or 10 joules per second. So, therefore, knowledge of fluid flow is a prerequisite to the calculation of convective heat transfer rates. While in conduction, as you have seen, there is no fluid flow involved. So, the rate law is a Fourier's equation, and we can therefore solve the governing energy equation, and without any knowledge of fluid flow, because there is no fluid flow within the solid, we should be able to predict. But before we can address convection, so therefore, we have to know about the fluid flow. And how do you know fluid flow? We know fluid flow either through experimental techniques. We insert a probe and find out the velocity, or as I have indicated in the previous lecture on fluid flow, that we have governing equations, and we solve those governing equations, which are nothing but Navier-Stokes equations. Okay, and once we solve the Navier-Stokes equation, we have a very good idea about the fluid motion in the system itself. And having obtained the fluid flow, having obtained information about flow in the system, we should be able to calculate convective heat transport, provided we have a similar energy, we apply a similar energy conservation equation. Now, the equivalent equation, and you must appreciate that the subject is getting highly quantitative now. Okay, and all this would be useful, when we would like to predict the melting rates of deoxidizers, melting rates of alloying additions, heat flow through the refractories, heat loss to the furnace mouth. All these theories are going to be useful, and you see, we talk of rigorous science here, are talking of energy balance. mechanistic approaches, we are talking of differential equations, we are talking of boundary conditions, and the subject is getting highly quantitative and complex as well. So, if I now do a similar energy balance, okay. So, what we have seen, we have net rate of change of temperature of the control volume is because of heat flow in net heat flux of heat in 3 different directions. But within a liquid, when heat flows from one point to another point, we have both heat conduction and heat convection, both are operational. Of course, if the transport is occurring over a very large distance, it is convection that predominates over diffusion or conduction, but nevertheless it is not correct to neglect conduction, particularly as you will see that suppose we are talking of flow of fluid near a wall. Now, near a wall, what happens? The flow of the fluid slows down because the wall is stationary, and as I have indicated when I was talking about fluid flow, that along the solid wall, okay, all the components of the velocities are 0. So, if the velocities are 0, so near the wall it is predominantly conduction that is going to be important. On the other hand, if you move from the wall to the bulk of a system, okay, the walls are here on both sides and we are talking of at the center. So, the influence of wall here is very little, and here we will see one point to another point, heat flow will be by convection, predominantly by convection. So, therefore, when you talk of if this element is a fluid element, okay, so and we are trying to make an energy balance, right, an energy balance expression. So, within this control volume, from one point to another point, heat will be flowing both because of conduction as well as both because of convection. So, therefore, we can understand that if I have to write a balance equation, energy balance equation for a fluid element where heat is flowing because of both conduction and convection, I will not have 4 terms on the right hand side, but I am going to have 7 terms. X direction, one conduction term, and on top of that conduction in x direction, heat will be flowing by convection also. Y direction, heat is flowing, for example, here only due to conduction, but now I am talking of a fluid element. So, in addition to that, I am going to have convection, and so is in the z direction. So, while the governing equation for a reasonably descriptive or reasonably realistic governing equation for a control volume in conduction for heat flow due to conduction may contain only 1, 2, 3, 4, 5 terms. You can see that if I am talking of conduction plus convection as the 2 modes of heat flow, in that case I may have 5 plus 3 more terms, altogether 8 terms. And now you can, once I write the equation, you will be able to appreciate the similarities between conduction and convection. So, let me just write down. So, I have the same term rho Cp, this is the accumulation term, then I have basically we write it like this. So, we have this now represents the net heat flux. This is the conduction heat flux, this is the convection heat flux, and this represents the net heat flow due to conduction along the x direction. And similarly, I can write the y direction equation. This is the conduction heat flux along the y direction, and this is now the velocity along the y direction. I should write Cp also, and then T, okay, and then I have the z direction flux, and then I have the volumetric heat source term. So, this equation typically is also written in this particular form. This is one way of writing, where this is the net flux, and net flux, as I have mentioned, net flux along x direction, because flux, unless you specify the direction, flux has really no meaning, net flux along x direction. So, finally, I can write this equation in this particular form, that, well, rho Cp del T. I bring in these negative terms to the left hand side, and then I say it is like this, I have the y direction term, I have the z direction term, then I put equal to term, and then I write down the same 3 terms which I am having here as the conduction terms. And so maybe I should write the third term so that you don't get confused here. So this is uz, the z component of the flow, and then what the difference between this is I have rearranged, I have brought this negative term on the right hand side, left hand side. So this is the rate equation. If I have to now, so this is again you can visualize it to be one equation and one unknown. Previous conditions stay well, rho, Cp and K are known, thermal heat source is known. So what is the unknown here? The unknown is T, only one unknown, one equation I am talking about, only one unknown, provided Ux, Uy and Uz are known. Okay. So given the velocity field, remember this, given the velocity field, given the thermophysical properties of the material under consideration, given the heat source term, this corresponds to one equation and one unknown. So therefore, if I have the right number of boundary conditions, incidentally this equation and this equation requires the same number of boundary conditions, because the highest order of derivative is 2, there also in x direction, here also along x direction. So I would say that given the right amount of boundary conditions, given the thermophysical properties, this is one equation and one unknown, and then I should be able to calculate or solve this equation and obtain the temperature field. And once I obtain the temperature field, what I can do? I can again make a plot like this, draw the slope and find out that what is the net flux because of conduction and convection together. So looking at this particular equation, I would like to make the one important point for you to note, that along x direction we have convection, along x direction we have conduction. Now this is a second order derivative, this is a first order derivative. This essentially implies that if I take a solid rod in which conduction is the only mechanism, physically this means if I take a rod, and in this rod, as you know that conduction is the only mechanism, if I hit the center part with a matchstick, the heat will flow along the rod in this direction also, heat will flow in this direction also. So that is the meaning of, you can go in this direction also, you can go in this direction also. But now imagine heat is flowing in this direction. So the fluid is flowing in this particular direction. So for heat to flow the large distance opposite to the direction of the flow is going to be very, very difficult. So this is the one way behavior of the term, this is the first order derivative. So the condition at a point will determine that what is happening on this side of it. Okay, it is not dependent on this side. So if the fluid is flowing on this particular direction, the heat at this particular point will depend on heat what is here. How much heat is here, that will determine how much heat is flowing here and not what is there. But on the other hand, if I am standing here, if I hit this point and this point, my temperature may depend on at what rate I am hitting here, at what rate I am hitting here. Okay. So this is basically the second order derivative, and what I have said about the nature of the flow in one single direction, that the downstream point has no role, and that is reflected in the first order derivative. Now solving this equation therefore will require, I have to solve for the ux, uy and uz field. So solve the velocity field first and use that velocity field to solve this particular equation. So it's a cumbersome task. Now let us imagine I have a solid. What is my objective? I have a solid which I have immersed into liquid. So this is a liquid bath, for example, and I want to find out that at what rate it is melting. So that means from the liquid the heat is going to the solid surface, and as I have mentioned that heat will be flowing to the solid surface by a combined mechanism of conduction and convection. So I have to solve this equation in order to find out this particular slope at the temperature profile in the surface, and then draw a tangent to find out the slope. So it is going to be a really cumbersome task in order to find out the rate of, so I have liquid here which is at a temperature of T, and this is a solid which will undergo melting, and this is at a temperature of T1. So T is greater than T1. Okay. So the heat is continuously flowing to the surface, and in order to find out the rate of melting, okay, I have to know the rate at which the heat is going from the liquid to the solid, and therefore, that rate can only be determined provided I map the temperature everywhere within the system, and at the surface I draw that kind of a graph which I have shown here, draw the tangent to the temperature versus distance profile, and thereby determine the net flux. So, it is going to be a very complex task. On the other hand, we can, there are empirical ways to find out that what is how much of heat is really flowing to the surface, and there we say that the rate at which heat is flowing to the surface, okay, it depends on, it is the heat transfer coefficient multiplied by area, and then I would say T minus T1. So, now this H, which is called a heat transfer coefficient, this is actually related to the fluid flow itself. Now, for very simple situation, people have found out that a similar very simple equation of this can be derived for a simple situation. Simple situation means I am talking about, say for example, I have a flat vertical plate and then the fluid is flowing past it very nicely in a laminar flow mode, everything is under steady state, okay, and this particular condition one can solve this equation by analytical means. That means I do not have to use any computer, I do not use any numerical methods, but I can solve it just following the procedure of solving of ordinary differential equations, and then I can find out the rate. And it is found out that the rate of flux, heat flux under those conditions, that from a hot plate at what rate heat is flowing to a liquid which is flowing past the vertical plate, okay, we can solve the convection diffusion equation, which is this is a convection diffusion equation or convection diffusion of thermal energy. So, you can solve a simplified version of this energy in order to get the heat flux, and it is found out that such a heat flux solution can be cast into this particular form itself, in which this parameter, which is called as the heat transfer coefficient, is a function of the velocity of the fluid. So, this result is obtained for some classical benchmark solutions by solving of this kind of a governing equation. So, this tells us that no matter what is the problem, even if you have turbulent procedure, turbulent flows, even if you have multi-phase flows, even if you have unsteady state behaviors in the system, it is possible that we need not have to solve those complex equations, but to express the heat flow we will have to heat flow to the solid surface, or from the solid surface we can use this particular rate equation. But here the task is now that how do you obtain the heat transfer coefficient, which is a function of fluid flow. The influence of fluid flow is coming into the picture, okay, and it is through this heat h term, which is small h, which is now basically the results are expressed in terms of where from the h is obtained. The results are obtained, for example, we say that in terms of dimensionless groups. So, Nusselt's number is a function of Reynolds number and Prandtl number. You see, your heat transfer, we are getting in and in into the heat transfer. These are dimensionless number, and this dimensionless number is nothing but heat transfer coefficient, characteristic length scale, and divided by thermal conductivity. And we must remember that this thermal conductivity is the thermal conductivity of the fluid phase. On the other hand, if you are talking about Biot number, which looks similar to Nusselt's number, okay, there the thermal conductivity is the thermal conductivity of the solid. Reynolds number, as we all know, it is. So, Reynolds number can only be calculated provided we have some idea of the flow, okay, and Prandtl number is again the thermophysical property. So, it is alpha. So, it is actually, I have written it reverse way. So, this is kinematic viscosity by thermal diffusivity, which I have just now introduced. This will be known to us because this is the properties of the fluid. These terms, characteristic length and thermal conductivity of the fluid, is also known to us. So, only uncertain parameter here is u, which is not known to us. So, somehow if you can acquire the value of velocity in the system, we can apply a correlation like this, and this type of a correlation is called forced convective heat transfer correlation, forced convective heat transfer correlation. So, if you know the velocity, then use a force convective heat transfer correlation and find out the value of h. Okay, h is unknown, h you have kept on the left hand side. So, this is treated as a dependent variable and these are independent variables. So, substitute the value of u into the right force convective heat transfer correlation, obtain the value of h, substitute the value of h here, and these temperatures which are known, the melting temperature and the liquid temperature, interfacial area is also known. So, we should be able to calculate the rate of heat flow to the surface. Now, we have force convective heat transfer and we have free convection heat transfer also. Now, there is this distinction. Force convection means, for example, if you are the convection heater, air conditioner, these are case of forced convection. Okay. So, if you have a fan moving on in a room, okay, and that causing heat to be distributed all over. So, we are using forced convection. So, therefore, in the context of steel making, I would say if I have a ladle which contains, and I have a porous plug here, and I start the contents of the ladle, okay, and there is a motion, and this motion is going to aid the distribution of heat in the system. So, this is heat will flow from one point to another point due to convection, of course, and that convection is going to be forced convection, and forced convection, the origin of forced convection here is gas injection. On the other hand, I can have a ladle with no gas injection, but that heat is going to be lost from all surfaces. Okay. This may going to give rise to some differential in temperature T here and T1 or T2 here and T3 here, and we can expect that T3 is going to be lower than T2 because T3 is closer to wall. So, now we can understand that temperature and density are related. So, higher is the temperature, then we can say lower is the density, lower is the temperature, higher is the density. So, differential temperature will cause differential density and heavier density material will sink down, lighter density material will rise up, and this will create a convection current, the origin of which is the differential temperature field. And this sort of a convection which precipitates in the system or generates in the system due to temperature difference is called free convection heat transfer. So, we have not forced, but then we have a free convection heat transfer. So, we either have a free or forced convective heat transfer correlation, and this sort of a correlation is for forced heat transfer correlation, forced convection, and Nusselt's number as a function of Grashopp's number, and Schmidt-Prandtl number is a free convection heat transfer correlation. So, depending on the scenario. So, your job when you want to calculate the net rate of heat flow, what is your job? It boils down to not to solve this equation, but to first identify the applicable heat transfer correlation to your case. Try to understand whether it is a free convection or a forced convection. Having understood that it is a case of forced convection, you understand the geometry of the scenario, whether it is flow over a spherical object, whether there is a strong one directional flow or multi-directional flow, whether it is a laminar flow or a turbulent flow. You try to understand the process or the flow and the heat transfer well, and then you try to look at the literature and find out that whether you have a correlation available to the situation which you are interested in. If you do not find such a correlation available, you have no option but to carry out experiments and find out that what is the applicable correlation itself. For example, we have seen this correlation maybe when you have done a heat transfer course. Okay, flow past a sphere, I think it is 0.6, Reynolds raised to the power half and Prandtl raised to the power 1/3, which is called the popular Range-Marshall correlation. Okay, and this too shows that it is applicable to a spherical geometry. All heat transfer and mass transport correlation, as we will also see, for spherical geometry, the distinguishing feature of the correlation is that it has 2 plus something, and this 2 corresponds to pure conduction, the pure diffusion situation. This component comes because of the presence of Reynolds number, which is the forced convection scenario. So, therefore, we can say that if you have the correlation already available, flow past a spherical object, it is to be understood that for all practical situations that we are interested in under steel making condition, a correlation may not be available, and that may really pose problems to us. So, therefore, assuming that a force convection correlation is available. Next would be to find out that what is a meaningful velocity scale that we have to use in that particular correlation. So, in this correlation, the moment I say that, well, the velocity in the Reynolds scale is known to me, it becomes a trivial exercise, because on the left hand side now there is only one unknown, and that unknown is the heat transfer coefficient. So, having obtained some information on the flow, I can calculate Reynolds number. Prandtl number is already known and fixed, and therefore, I can calculate Nusselt's number, from which I can calculate the heat transfer coefficient. Substitute the heat transfer coefficient in the rate equation, and then I should be able to calculate the convective net heat flow to the solid object, or the net interaction, thermal interaction between the solid and the. Now, during melting, we must understand that solidification as well as melting is going to take place, particularly when you project a solid into liquid. Now, for example, if you project this solid into a liquid, and this solid has a room temperature, is a deoxidizer element or an alloying element. So, typically you form a solid crust. Now, this crust, when the material is under liquid, submerged in the liquid, this crust melts back. Okay. So, initially there was no crust, so some solidification of crust takes place, then the crust melts back, and once the crust melts back, then the original solid is going to be exposed to the liquid. So, it goes like this. So, the solid is coming, I can say this is a solid. The next stage is you have formed the crust, and the third stage is maybe again the solid is exposed. So, this is the initial radius, the radius has increased, the radius has decreased, the original radius. So, here and here the radiuses are same, and this duration from here to here essentially tells us about the shell growth and shell melt back period, and then finally the size decreases, and eventually the object melts and vanishes into the system. So, the R versus T curve, radius curve in this case is going to be something like, if this is the original radius R0. So, for some distance the radius goes like this, increases, and then the radius decreases. Okay. So, therefore, this is the duration, you see. So, the radius as a function of time, the radius increases, radius attains maximum value, and at that particular point the formation of shell is complete, the shell now starts to melt back and radius decreases, and at this particular time the original sphere is released. So, this is the duration which corresponds to shell formation and shell melt back, and this duration from this point onwards to this represents now the melting time of the alloying addition itself. Now, therefore, in order to calculate this, okay, we have to take into account the latent heat of solidification as well as of latent heat of formation, and also we must solidification and melting, one is positive, another is negative, and we must also first understand that the geometry of the object is not constant all the time. So, this area that I have used in the rate expression will not remain constant during the melting scenario. Okay, this is going to continuously change as I have indicated. So, if you take pi r square, which is the, or 4 pi r square, which represents the surface area of a sphere, it is understood that 4 pi r square is going to continuously change during the process. So, taking an initial area is going to be highly misleading in this particular case. So, this A is going to be a function of time. Now, therefore, the task is really not as simple as obtaining the value of heat transfer coefficient and then substituting it into this equation and this, and this is called a typically moving boundary problem. Okay, when you have a solid whose size is changing because of the processes taking place in the system, and then the boundary or the domain in which you are interested, because you want to find out the complete melting time of this particular addition. So, you want to find out the rate at which it is shrinking, and therefore, the entire time duration has to be taken into account in order to predict that time realistically. So, we have to now take into account that, for example, if I say that I want to write down the equation, heat flow equation within the solid. So, the same conduction equation that I have written will come here, rho Cp, and if I say that, well, it is only one dimensional heat conduction. Within the solid, there is a radial symmetry. Okay, so heat is flowing along the r direction. Theta and phi are not important. Spherical coordinate system is what? Spherical coordinate system is r, theta and phi. So if there is theta and phi symmetry, I can say heat is flowing in the radial direction, and this is actually 1 by r square. This is the governing equation, k r square. Now, as far as this equation is concerned, I have to give some condition that at r is equal to, I require that, because this is a derivative in terms of r, this is a second order derivative with respect to r. So therefore, two conditions on r. I need a condition at r is equal to 0, which is well known. This is a symmetry condition, and I need a condition at r is equal to some point, but that the radius itself is changing as a function of time. I will not be able to apply boundary condition to this equation in a exact manner. So from somewhere the value of r is to be calculated, and that is an energy conservation statement of energy conservation at the surface of the solid, that the net rate at which heat is flowing into the solid plus heat which is evolved or consumed here because of the melting and solidification phenomena plus the heat which is flowing because of conduction, all three things have to be taken into account, okay, in order to predict the temperature profile within the solid or melting time completely. Note that in the first equation no information is there on the fluid flow itself. How does the fluid flow part gets into the equation or the process mathematically? It is because the flow of heat at the surface, I require boundary conditions. So through the boundary conditions to that equation, at, for example, if I say that at r is equal to r1, which is at a particular instant, suppose this is the radius of the vessel, I can say the rate at which heat is flowing I can be given in terms of this heat transfer coefficient, which is the convective heat transfer coefficient. So through the boundary condition I will be able to incorporate the effect of fluid flow. Now therefore, this equation alone I cannot solve in melting problems. I have to solve this with an expression for the change in size, and therefore additional energy conservation equation will be necessary. So two equations and two unknowns. What are two unknowns? The one unknown is the temperature, and the other unknown is the changing geometry of the object itself. So therefore, I will have an energy specific energy conservation equation. I will have a heat conduction equation. These two equations I will couple together, and then I have two equations and two unknowns, and as a result of which I should be able to predict temperature as well as radius as they are changing as a function of time, and based on such I will be able to calculate that what is the complete melting time. So the subject is getting extremely complex, and if you can remember, these are single objects immersed in a fluid. If you have multiple objects, multiple phases, turbulent flows and all these kinds of things, the task is really complex, and you have to have very good background in heat transfer, in numerical techniques, in fluid flow theory, in order to calculate convective heat transport fairly realistically.